Hello all, welcome to my course on methods of adhesion measurement, theory and practice. Today we are at lecture 16 and we are discussing about contact mechanics, Hertzian mechanics. So, we have started that topic in the last lecture. Today we will continue with that, and if possible we will also start talking about some idea of surface and interfacial energy, and that way we will introduce the topic of adhesion. So, remember that we discussed in the last lecture that we have these two solids of non-conformal surface and non-conformal contact, and let us say that those solids are in contact at 0 load, there is a point contact. So, now let us say that we talk about two solids of revolution in point of contact, okay, and contact load between them surfaces are 0. These two surfaces are represented by S1 here and the S2 here. So, S1 here and S2 here, and so from this particular plane let us say that this particular point is a xy. So, from this particular plane the height of this surface is Z2 here and this surface is Z1 here, and so therefore, the distance between these two surfaces at this particular point axy can be written as Z1 plus Z2, which is that contour that we talked about in the last lecture hxy. Now, the applied load on solids in contact. So, now let us say that we apply the load on these two solids in contact. What happens? So, what happens is something like this. So, suppose that we have applied the load over here, this P here, and so the equal amount of load is being applied over here, P here, and these two. So, now because of this application of the load, this point of application which is far away from this point, they were in contact, they move. Let us say that this point has moved by distance delta 2 here and this point has moved by distance delta 1 here. Now, what has happened is something like this. Let us consider an hypothetical situation in which the two solids have simply gone moved ahead, okay, by the distance delta 2 and delta 1. So, what it means is that this particular surface which was represented by S2 was initially over here. Because of this point of application moving by distance delta 2, it has come to here, this particular point, and then we have this surface that is S1 which was over here, and because of application of the load this particular surface has gone over here. Let us say this is a hypothetical situation. So, as a result what has happened is that the distance between different points, distance between the points, let us say that this particular point is over here, okay, which was at axy. So, axy was the point in my last slide. So, the gap between these 2 points, gap between the two surfaces at this point, right, vertical distance between these two surfaces at this point axy, okay, this was hxy, and now that these two surfaces have moved towards each other, okay, by distance delta 1 plus delta 2. So, delta 1 plus delta 2 is the distance by which these two surfaces has come closer. So, initially the gap was something like this, let us say, okay, now they have moved closer. So, the gap is now decreased. So, the gap is now is this particular quantity. So, therefore, this quantity is hxy minus delta 1 plus delta 2, that is delta over here, right. So, again I repeat. So, let us say that initially this particular surface was S2 was here and S1 was here, and now the load has been applied, that is P, and because of that these two solids have moved towards each other. And let us consider a hypothetical situation in which these two solids have moved like that same way as these distant points. So, as a result this solid S2 that has moved over here delta 2 over here and S1 delta 1 over here. So, as a result that this point the initially the gap was hxy and now they have moved closer, this particular distance is hxy minus delta 1 plus delta 2. Now, it cannot be possible that they cannot move just like that, because if at some locations the two solids have gone inside each other. So, for example, in these positions, okay, what will mean by this hypothetical situation that these two solids have gone inside each other. Now, that is not possible, okay, because these are two solids, they cannot go inside. Now, so therefore, what has happened is they have actually deformed, and they have deformed such that they have got now a finite contact area given by this 2a as the width. So, if at location the two solids have gone inside each other, that is not possible. So, the two solids have undergone vertical deformations. So, for example, that the solid 1, okay, that has gone a vertical deformation of let us say V1 at z is equal to 0 and V2 at z is equal to 0, okay, they have undergone the vertical deformation. So, what it means is that over here let us say that S2 surface over here, okay, that has deformed by this distance, okay. So, that is their vertical deformation. So, means like the S2 surface is over here and the load has been applied. So, therefore, this has become something like this. So, that means at these points, this has undergone the vertical deformation here, that is V2, let us say at z is equal to 0, and similarly this is the S1 surface, and then S1 surface has become something like this over here. So, they have undergone the vertical deformation here V1 at z is equal to 0, something like this. So, as a result, this finite contact radius have formed, and so what has happened is at this point a x y, the distance between the two surfaces has now decreased to 0, let us say. So, this particular point, it lies on this particular surface contact area a x y, okay, such that now the distance has become is equal to 0. So, what it means is that when the deformation occurred V1 and V2, so at this point the surface actually moved away from each other, okay. So, over here for example, the surface initially was here, then it away from each other, right. So, therefore, what has happened is now that the gap between them has increased. So, it decreased from h y minus delta, and now that there is deformation that have been allowed, vertical deformations. So, therefore, the gap now has been increased, and now it has come down to 0, because why? Because this particular point is now at this contact area, that is why. So, the points which lie on this contact area, okay, for all these points, this condition gets satisfied, that h x y minus delta. So, minus delta is this delta 1 plus this delta 2, okay, and that is h x minus delta plus V1 z is equal, that means if I am talking about this point. So, at this point what is the vertical deformation that has happened to the surface of these two bodies 1 and 2. So, that is V1 at z is equal to 0 and V2 at z is equal to 0. So, this has to be equal to 0 so that this point lies on this contact area, and if the point of solid at these points they are not in contact, then this is the gap is still positive. So, therefore, it has to be greater than 0. So, the points where the solids are not in contact, the distance between them is greater than 0. So, it is like that. So, that is the way it has been argued, and so we can write something like this. You see h x y minus delta, okay, plus this plus V1 at z is equal to 0 plus V2 at z is equal to 0. So, the whole thing is equal to 0 here, and so therefore, this V1 plus at z is equal to 0 plus V2 at z is equal to 0, that is equal to comes out to be delta minus h x y. So, remember that h of x y, okay, I have written it as a x square plus b y square. So, a b are those functions of those relative radius, inverse of those relative radii of curvature, right, that we deduced in the last lecture. So, here V1 at z is equal to 0 plus V2 at z is equal to 0. So, that will be equal to this delta minus a x square minus b y square. We can do a little more algebra here, and we can write this delta 1, okay, as V1 at x is equal to 0. So, what it means is that here whatever is the delta 1 that happens at this particular point, okay, so that is at x is equal to 0. So, delta 1 in essence is the vertical deformation of this surface at x is equal to 0, okay, here x is equal to 0, like that. So, we can write this delta 1 and delta 2 as like this, and so therefore, okay, we can write it as V1 0. So, basically delta, so we can write it like we can take this quantity, this part, and the left hand side and the rest on the right hand side. So, therefore, we will have here let us say V1 minus V1 z is equal to 0 minus V1 at x at any x, and then V2 at z is x is equal to 0 and V2 at any x, right. So, this quantity, so that directly comes from over here, and that will be equal to half of a square this ax square and then plus by square, and the a and b are defined in terms of this relative radii of curvature. So, like that. So, see, we just derived in the last class the last lecture the relative radii of curvature, and that is the idea that is being used over here. So, that is the good thing about it. So, now I just mentioned about this, consider two solids of revolution. So, we had discussed what we are discussing about two solids of revolution. What are the solids of revolution? So, I need to say a little bit about that. So, the solids of revolution, a 3-dimensional shape that gets created by rotating or revolving a 2-dimensional shape around an axis of rotation. For example, this is an area, let us say surface area, right, and that surface area we rotate it about this x axis over here and we generate this conical structure. So, this is conical 3-dimensional shape. So, that particular surface that has been generated now, this conical surface, okay, that is called the solid or the conical object that has been developed by that is called the a solid of revolution. So, for example, over here again that this is the area which is being revolved around this x axis, and we get finally this particular object which is also a solid of revolution. So, we are actually discussing about that solid of revolution. Now, let us say that solid of revolution for our case are spheres. Let us say we can we said that I am going to discuss two simple geometries. So, a sphere is one such geometry. So, in that case this we have derived earlier, or like we can derive that r1 dash and r1 double dash will be equal to r1. So, there are two spheres, one is of radius r1, another case radius r2, and then their relative radii of curvature also can be obtained, and their radius their principal radius are equal, that I discussed earlier. So, the principal radius, the maximum radius, revolution, maximum radius of curvature, minimum radius of curvature, both are same, that is r1, and in this case this is r2 over here. And for this sphere, okay, the two spheres, the relative radius of curvature will be 1 by r is equal to 1 by r1 plus 1 by r2, that way. So, what we have just derived, that V1 at z is equal to 0 plus V2 at z is equal to 0, that is equal to delta minus ax square minus b y square. Now, since it is a sphere, so instead of x and y axis we can have r theta axis, and so therefore, we replace x and y by r, and we have we can write in the values of a and b here. So, that will come out to be let us say 1 by 2 r. So, we will have delta minus r square by 2 r. Okay. So, that is just a extension of this particular equation that we have derived just now in the xy plane, but we can do it on this rz plane with the theta as the theta symmetric, and so we can get this delta like that. So, delta minus r square by 2 r. So, the displacement, okay, V1 at z is equal to 0, V2 at z is equal, so that means at any point, okay, the displacement over here. So, the displacement then let us say any point, that is V1 at z is equal to 0 plus V2 is equal to V2 at z is equal to 0. Okay. So, the total summation of that can be written as delta minus r square by 2 r. Okay. That is the thing. So, now so far so good. So, delta minus r square by 2 r. So, how do we get that? Okay. What kind of stress profile at the contact area will give rise to this kind of displacement field? That is what is the question now. So, that how can I relate it, okay, to the topics that I had already studied in the last few lectures. That is what we are going to show now. So, let us say that we have to make few assumptions over here in order to connect what we are talking about today to what we had talked about earlier. So, what are these assumptions? So, now one of the thing is that R1 and R2 are much larger than R here. So, the R here is that contact radius R or A, whatever, I should say A also I can say. So, let us say this contact radius, okay, A here or R whatever. So, it is R1 and R2 is much larger than R. So, that means the stress field that I will be calculating, okay, on the basis of a solid is infinite in extent. So, means like with respect to the stressed region, the solid is actually much larger. So, the solid is much larger over here, stress I am detecting something over here. Okay. So, as far as this region is concerned, this is actually a flat surface. Okay. This particular portion is part of this whole this solid revolution, but remember that this quantity is much smaller with respect to this radius of curvature, and as a result, okay, whatever I am seeing here, okay, this is this actually is a flat surface, that is the thing. And this then the surface outside the contact region is roughly approximate to a plane surface. So, here the radius of curvature is very large. So, I can consider, I think that, so this capital R is much greater than R. So, that means the relative radius of curvature is very large. So, therefore, we will consider that the outside surfaces outside the contact region is also roughly approximate to this plane surface. So, that is one consideration. Second consideration will be that strains within the loaded region are sufficiently small to remain within the linear theory of elasticity. So, that is important, because whatever we are discussing, okay, that stress strain relation, Hooke's law, okay, the relation of the stress strain is equal to let us say normal strain is Exx is equal to del u by del x and blah blah all that. So, those are all fall under the linear theory of elasticity. Therefore, we have to assume here that the strain which is there within the loaded regions are very small. So, that is important. Now, these are consequences of this. Another consequence of this assumption is that the changes in the boundary forces arising from deformation. Okay. So, that means that when you apply the strain, there are deformation that is happening. So, this deformation in itself is produced small enough that it is not changing anything. I mean, like the stress field outside it or inside it, or like this is a in a linear regime. Okay, not in a non-linear regime. So, it is quite small, that is important. And then is that it is assumed frictionless, so that only normal pressure is transmitted between them. So, as I was telling some time back, that there is no asperities and there is no waviness about this contact, and so therefore, the surface is completely friction smooth, no friction and no asperities. So, therefore, the force that gets transmitted between them is basically normal pressure, and there is no friction between them. Now, under these assumptions, we can think that each surface is an elastic half space with a circular or elliptic loaded region. Okay, that is the thing. So, that is the thing here, that we are talking about two curved surfaces. We are not talking about the elastic half space that we have discussed earlier. Remember that. Okay, before last lectures and all that, we are discussing elastic half space, but here we are discussing a curved surface, so a curved solid, a solid revolution. But then in the case of solid revolution also, Hertz assumed that the results, okay, which we derived for this elastic half space can be valid if we can make this kind of assumptions. That was his idea, and therefore, okay, once we have these assumptions, we can actually consider that each surface is an elastic half space, and the loaded region is what? That is, let us say, a circular region, because let us say I am talking about two spheres in contact. So, if the two spheres in contact, the contact area will be a circle. So, therefore, it is fine to think that it is a circular loaded region. And remember that while we are discussing about a point load and the elastic half space, point load or a distributed load, we discussed about this circular loaded region. We will show this once again now. We can then use the results derived earlier, that is the important thing about it, right. So, we have derived whatever we have derived earlier, now it is being useful, because now we are indeed discussing a curved surface, and there those results that we derived for elastic half space will be useful. So, remember that we discussed about these three different pressure distribution at the contact area, a circular contact area. So, in one case we had the uniform pressure P is equal to P0, second case we had this kind of pressure distribution, okay, P0 into 1 minus R square by S square or T square by S square square root, and here I had this stress singularity at the edge. So, that is P0 into 1 minus R square by S square and to the power minus half, and if you remember that these were for a punch, flat plate punch, right, and this for this case we had a parabolic surface, parabolic indenter that we get, and the vertical deformation within the loaded area contact area came out to be like this. And for this case P is equal to P0, the vertical deformation, okay, in the loaded area, that is r less than equal to a, that was that elliptic function of the second kind that we had gotten, right. So, here this v at z is equal to 0, 1 minus sigma square, that is the Poisson ratio square divided by Young's modulus, and pi p 0 by 4 a. So, this we have derived into 2 a square minus r square. So, this result, okay. So, now if you see here that this quantity, the total, this deformation over here, that is equal to delta minus r square by t 2r. And if you see this two relations, all these three relations with this relation, okay, in which case, okay, there is match between these relations and one of these relations. So, you see here very clear, here it is constant, here the displaced deformation is constant, it is a flat punch constant, here is an elliptic function, okay. However, here there is a parabolic profile and there also a parabolic profile. So, what it means is that the load distribution at the contact area for this case of two solids of revolution in contact is essentially this, p is equal to p 0 into 1 minus t square by a square r square by a square square root. And so, that is what we have to consider here, and we have to see that what is the, let us say that this is V defines the total load. So, we will soon see how it happens, and then we can compare, okay, this relation with this relation over here. So, that is what we can do here. So, that is the thing here. Now, pressure acting on either body is equal, we therefore add the respective displacement on body 1 and body 2, that is the thing we will do here. So, for example, we can write that V at z is equal to 0 is equal to 1 minus sigma 1 square by E 1 into pi, this is p 0 by 4 a into 2 a square minus r square, and then V, it is 1 here and this is V 2 here at z is equal to 0, this is equal to 1 minus sigma 2 square by E 2 into pi p 0 by 4 a and 2 a square minus r square. See, all other terms remains same, because the p 0 of the total load pressure, that is actually same, and that depends only on a, right, that is there. If you remember that p 0, the total pressure that is applied depends upon p 0 and a over here, and so a is same for because that is the contact radius. So, if you add up, then we will have V, okay, at z is equal to 0. So, that will be here 1 by E star, for example, and let us say it is pi, and this is p 0 4 a and 2 a square minus r square, and where 1 by E star, okay. So, that will be equal to 1 minus sigma 1 square by E 1 plus 1 minus sigma 2 square by E 2, like that, right. So, it is called the equivalent modulus, right. So, that is what it is, equivalent elastic modulus. And so, now if I compare, okay, these two relations here, and I really like to do this. So, delta here comes out to be 1 by this E star into pi, this is p 0 by 4 a into 2 a square. So, this is equal to, this is 1 pi, this is p 0, this is a here, this is 2 here, and this is E star here. So, this is 2 and then E star here, pi p 0 and a here, like that. And over here this is delta is equal to this, right, and 1 by 2 r, 1 by 2 r. So, that is equal to this term 1 by E star into pi into p 0 by 4 a, pi into p 0 by 4 a, that is 1 by 2 r, and so 1 by r can be represented like this. So, a can be represented in terms of r. So, let us do that. So, here I can do a will be equal to, this is pi equal to pi, this is p 0 by 4 E star over here into 2 r. So, 2 gets cancelled. So, it will be 2 r here, 2 E and r here, like this. So, here this is the way, this is the relations that you can derive, and we can write this P0 in terms of total load that I was telling you that with this particular relation or this integration I have already done in one of those previous lectures. And so, here this capital P can be obtained by P bar 2 pi r dr. So, that the load is throughout this area, this is r, let us say. So, this is r plus dr, the radius over here, and then we integrate and all that. So, we have done all that once, and so therefore, P. So, we can instead of P0, okay, we can substitute over here, and we get all these relations which you can verify, and these are directly comes out. So, here this A is something comes out to be in terms of this capital P, capital R and E star, and capital R 1 by R will be written as 1 by R1 plus 1 by R2 and all that also you will get. So, that is the results that we have. So, let us solve one problem. So, small sphere with radius R1 is equal to 5 millimeter and larger radius of R2 is equal to 20 millimeter are in contact under a load of P is equal to 1 Newton. Both surfaces spheres are made of steel, steel cannot be so low modulus, some rubber let us say with E is equal to 2 megapascal and sigma is equal to Poisson ratio equal to 0.3. Let us say it is some rubber here, it cannot be steel, cannot be 0.2 megapascal. Now, compute the radius of the contact area between the two spheres and determine the maximum contact pressure, and extend the analysis to include an additional load. So, that is another part, I am not going to do this part, this you can do on your own, but this part I have done. So, here 1 by E star will be represented as 1 minus sigma 1 square by E1 plus 1 minus sigma 2 square by E2. So, you substitute that E1 and E2, E1 E2. So, both are actually 2 megapascal and 0.3 is the Poisson ratio let us say. So, it comes out to be 1.1 megapascal. You can do little algebra 1, and then relative radius of curvature is 1 by R, that is given as 1 by R1 plus 1 by R2, and that comes out to be simply R is equal to 4 millimeter. And so, like that. Then a contact load is P by 1 Newton, and we write here P is equal to 1 Newton. So, we want to find out what is the radius of the contact area. This relation we have already derived, where it is here is to the power 1 by 3, remember. So, A, so that is the interesting thing here, A okay, is goes as P to the power 1 by 3 for a spherical contact, and later on we will see for a rectangular contact this A will goes as P to the power 1 by 2 like that, for a cylindrical 2 cylinders in parallel. So, we will discuss about that when it comes, but here it is A goes as P to the power 1 by 3, so like that, and so here this A will be come out to be 1.4 millimeter. So, the maximum contact pressure is equal to P0 equal to capital P by pi a square, and it can be written something like this. So, that is the way, by using those ideas you can actually solve this kind of problems. There is another problem I have not discussed about cylindrical rolls. So, I am not going to talk about here right now, I will take it up this problem later on, but you can also try it like that. So, that is all I have about the about this Hertzian contact mechanics. I said that I will briefly touch upon the force of adhesion and surface forces, and then I will start from the next lecture more detail about this adhesion aspect. But just to begin with, that two materials, okay, irrespective of their chemical character, they actually attract each other, okay. And so, this particular effect was seen by van der Waals in 1873, and he proposed the concept of general attraction between neutral atoms. So, if there is a non-neutral atom, that means let us say there is a polar molecule. So, polar molecules will always can attract or repel each other, but these are actually between neutral atoms to account for certain properties of non-ideal gases and liquids. So, the ideal comes from the ideal gas, and when there is a non-ideality, the ideal gas law fails, and there van der Waals proposed that there is some general attractiveness, and then there are different phenomena which are contributed to these van der Waals interactions. So, that is what we would like to talk about. There are three kinds of interactions, and one is called the dipole-dipole, another is called dipole-induced dipole, and another is called fluctuating dipole-induced dipole. What are these, how they work, and we will not go into the whole lot of maths around them, but we will try to understand that conceptually what are these different types of forces or interactions, and how that affect adhesion, and how the adhesion is dependent on the great distance between these two surfaces which are being acted on by such intermolecular interactions and all that. So, that will come in the next lecture. So, thank you for your kind attention.